Hey, so welcome to today's lecture in neural network and deep learning. What we will do today is we'll finish with the state space models, look at two additional variants of that, and then finish the part on architectures by looking in generally again on sequence models, how we then maybe can combine them, giving a bit of an overview on the sequence model that we have. But I will start with a short repetition of the challenges on the time invariant models, and then we'll go to time variant and continuous time state space model. We saw that on the one hand, these models are very nice. So this is like in blue, the transformer, and we had the linear RNN, the S4 in yellow, in orange. But so this would indicate, wow, this is really like significantly better than what we had with transformer, and that's a quite nice property. However, we also have a challenge, and this is here on text, where we might be also interested on, where the picture is a bit different. So the first one is an attention, while the next four in this case are different state space models. And what we're seeing here first on the positive side, maybe, so even the attention has the lowest number of parameters, the others are typically faster. So in order to compute, the state space models are very good. But if you look on overall here on the perplexity, where lowest numbers is better, you see that their attention is still somehow the best. And that, of course, gives rise to the question, what is somehow missing in these types of state space models? And people looked at two things which we haven't addressed yet. So we had our overall state space models, where the hidden state is a linear combination of linear transformation of the previous hidden state plus some transformation of the input, and then we get the output by, again, a transformation of the hidden state. What these models cannot do is like they cannot do some type of filtering. And maybe in a lot of applications, this might be essential, that we're not treat every input the same, but that we have a bit the ability to filter out some text. So for example, if you think about text and you are processing web text, there's a lot of junk in there which we might want to ignore. So, but each input is somehow treated the same. It's not that we can somehow decide, oh, this is not really important information for us, please ignore that. In contrast, if you think, for example, of the attention, you can focus on some part and ignore the other part, and therefore, like say, okay, this might not be relevant at the moment. Please only focus on this part. So this is like one challenge. Very similar if we're not looking at B but at A, so the metrics between the similar states, we're also not able to really like restart our history. So it may be that sometimes it's important that we forgot everything what was before and we are just starting. That can be, of course, at the beginning of an article. If you just have a text and now something new starts, maybe you want to forget a lot of things. Can even if you are focusing on specific things. So think about the quotations again. If you want to somehow control if you're currently in a quotation mark or not, you also have to be the ability that at some point you just forget what was before. Now we're inside the quotation mark. And then maybe you at some point restart and do that again. Or if you have these counters, which should somehow measure where you are in your sentence. So if you then have a sequence of sentences, you also would like to have that the counter always restarts when the sentence is over. So this ability of reset is not really possible because the history is always treated the same. It's not like depending on what where we currently are. The history is dependent. It's somehow always treated the same. And so this leads then to the question, can we do something else? And one way of treating it differently are the so-called linear time-variant systems. Before we are looking at an idea, do you have any idea how we could now address that? There we want to not treat every input the same, but like do a bit of like different treating of the different inputs. Do you have some architecture we discussed where something like that could have been done before? Any ideas? Yes?
Could use a classifier and a mixture of experts.
Yes, you could also do that. That's already a bit more complex. We first will look at something which we already covered in the lecture and which can do something that is able to do things here.
We could use like forget gates like in the LSTM.
Exactly. So in the LSTM, if you remember, we had a bit this thing already. So there we also wanted to store things for a long time in the cell state and only then like at specific positions do something. And there we had these three different gates, the forget gate, the input gate and the output gate, and they were also controlled by our current input. So somehow similar, we would like to do it here also, that we can control whether we are want to reset at the moment or whether we want to ignore the current input. And this gating architecture somehow allows that. So if we have a gate at the input, deciding whether this input should be in or not, there would be a possibility to do that. The same for similar output and for gate gate. So this somehow is a motivation which we are trying to in some way add now. The challenge is that we can't directly take the LSTM. So this has the disadvantage that we have a nonlinear recursion in there. Remember that these things were nonlinear, and therefore we can't do the parallel processing. We saw last time the nice thing about linear things is that we can roll out the network, and then especially during training, we can do things a lot faster, and we don't have to process one by one. So we can't directly do that. So because here you see that, if you remember, for example, the output gate is controlled by the previous hidden state. So there is a nonlinearity in there, and we can't do that. So we can't directly take our LSTM, but we will have a look at that and try to take some ideas from that to do this type of controlling. How are we doing that? So in generally, in the linear time variant systems, you see that we have some new letters in here. So we have AK, no longer A, but now we have here AK. We don't have B, but we have BK, and we have not C, but we have CK. So it's no longer that we are always applying the same A here in your picture, but we have different A's, which allow us to now not always do like treat the history the same way. We still have to store all the history somehow in a state, but then how this history is combined with our current information might be different because it depends on our current AK. And the same is true for B, and then we can combine it. So, and these A, B, and C, we will calculate are based on our X. So based on our input, we will decide whether we want to take this input, whether we want to take the history or reset. And then we can like do that, for example, in some type of network again, and we can reset, for example, everything by just having a model which will generate an AK which is 0. Or we can filter out by having a BK which is 0, because then this B is ignored. So we have the ability to do exactly this, to reset and to filter, and still do like some other the parallel fast processing. Now we said that AK, BK, and CK is based on input. What you have heard before, normally in the LSTM, for example, we also had it, I mean, it would make sense to that also depend on HK, for example. Why are we not doing that? Yes?
Because then we would need to parallel the trade.
Yes, exactly. So if we would have the MLP is typically nonlinear. So if you put HK into there, then, or HK minus 1, then HK is no longer like linear combination of the previous one, and we couldn't do all our calculating. So since we have a nonlinearity in the prediction of AK, BK, and CK, we can only put X into it, but we can't put the previous hidden state into it. So that is an important difference to the LSTM. There, as we saw before, the forget gate and the input gate, they depend not only on the input, but also on the current hidden state. So in some way, we're weaker here. We're not depending on our previous hidden state, but we're only depending on the current input. But this comes with the advantage that we can do, again, the parallel processing. So this is the overall somehow picture of the linear time variant systems. Now we want to look at two things. On the one hand, how we are doing the implementation. So if you remember, we had this parallel scan, which can do parallel like do the calculation. This does now look a bit more complicated, but because before you always had the same operation. Your new hidden state is like A times the previous hidden state and so on. Now we have different A's on it. So the operations are different in each position. So we first have to look, can we still do this type of parallel computation or not? And then in the second look, we will look at different ways of how we can exactly use AK, BK, and CK, how that can be implemented. Okay, so how can we do the parallel scan? So what does a parallel scan mean? We wanted to have this computation so that we can do calculate our last hidden state by always combining two hidden state in a tree-like structure. And then we can, if you do remember, we can do the pass up and pass down and be a lot faster in the calculation. In order to do this now, we have to use a bit of a trick. So instead of taking just xk, and then we could always do like the calculation by the hidden state is a times xk plus the hidden state, we have now a bit of a different operation. So at each state, we're not only storing the hidden state, which in the first position is bk times xk, because this is 0 at the beginning, but we're also storing AK, our matrix. So somehow the elements we are doing our operations on are now tuples, which are AK and BK plus XK. And then the addition, so the operation we do to combine two elements is, on the one hand, we are multiplying our two AKs, which means, okay, this is now the matrix that you need to put next time in front of your hidden state. Because of course, this matrix always gets larger and larger. And the hidden element is our A from the one element plus the second element, the hidden state, plus then the second element from the other. So this is exactly here the calculation done there. Let's do that step by step. So what we're initializing in is like our first element is A1, B1, X1. The second one is A2, B2, X2, A3, B3, X3, and A4, B4, and X4. So this is like how we initialize everything. So the big difference to before this was X1, X2, X3, and X4. So now we are doing the same type of operation on the 2D space, not on the 1D space. And we have a specific type of how we add up two elements, so how we're going up. And exactly this type of calculation we're doing now. So we are applying this operation. So if you're to combine this one and this one, according to this rule, this is A2 times A1. So this one times this one, so we have this element. And then it's A2 times this one, so A2 B1 X1 plus this one plus B2 X2. And you see this one at the end is now exactly the hidden state at the second position. This is the hidden state at the first position. This is the hidden state at the second position. We're just doing the same thing for 3 and 4. So here the combination is then A4 times A3. This is the matrix we have to store. And the value here is A4, B3, X3 plus B4, X4. This is not really a hidden state because in the sequence, we're never combining directly 3 and 4 because in the sequence, it would be always 1, 1, 2, 1, 2, 3, or 1, 2, 3, 4. But we're doing this pre-computation in order to then faster do our whole sequence so that we only need a log number of operations and not a sequential number of operations. Now we are doing the same thing, but now with the two combined states already, and you're seeing the sequence gets now a bit longer, but our new matrix here is then A4, A3, A2, A1. And the other one is you take the second A, this is this, multiply it with this one, then you're getting the first two terms, then you're adding the last two terms here, and that's the overall. That is then H4. So again, what we in the end have is the last hidden state, and you're seeing now that you're exponentially going here. So you have H1, H2, H4, and then if you're going the next layer, it would be H8, which is like showing you a bit the advantage and how you're doing it fast. In order to calculate H3, how will you do that? Any idea? Yes?
You reverse the operation taking A4 before F4.
No. We had last time, if you remember, there were two parts of these algorithms. Yes?
Down sweep.
Yeah, yes, exactly. So we have to do the downsweep. Then we get, I mean, then you maybe get H3 if you do the inverse operation. But the nice thing is you do first an upsweep and then a downsweep. You will really get all n operations. So not only every second and then like exponential number of points, but you get really all in the one we did the downsweep after. And you have to do exactly this type of downsweep operation then, now just on the 2D space and not on the 1D space. Good. Any more questions on this type of implementation? So we are using the same speed up. Again, we have all in training. I mean, this is only, of course, applied in training because there we have all our inputs available, and then we can calculate directly all the hidden state and don't have to go sequentially across the sequence. Yes?
So if you, for example, choose a certain matrix, then maybe if you have a space of 10 matrices available, and you always choose one matrix and always only train that, then the other ones are uninitialized, or rather only at the initialization. So if you choose them, your model will probably perform worse than if you just always did the first one.
Yes, exactly. That's why we're not having A1, A2, A3, but we're using a parameterization where this depends on your input. And so this is exactly the next one. So I'll give you one example. So the open challenge is exactly as you said. We can't have like fixed ones A1, A2, A3, because then, as you correctly said, if you would do that, you wouldn't train the long ones. So how we're doing it is we're trying to predict A1 and so on based on our input. So there are some parameters, but the A is different depending on what is the input value. So you have a general matrix A, and from this general matrix A, you're building now different versions of A depending on your input. And thereby you're getting the different versions of A for different inputs, and they are different. So A1 is not, that's maybe also an important thing. A1 will not be always the same, but depending on your input sequence. That's also important if you think about filtering. You not only want to filter based on position, but you want to filter based on content. How we're doing that, we'll look at 3 different examples. So the first one is this called a Griffin, where we try to predict them. And we're again having some type of gates. So what we're having here is we have our current hidden state and we have our input. Based on our input, the first one we are calculating is 2 gates. And these are even here in this case scalar values. So we have our recurrent gate that decides on how much information we are taking on from the previous one in order to do a reset, and we have our input gate, which decides how much input do we take. Based on our recurrent gate, then we are calculating this matrix AT, which is some diagonal matrix A, which are parameters to the power of C times RT. So mainly what RT decides is how often how you exponentially use this diagonal matrix A. So this is like how you parameterize AT. And then for your input gate, you see you multiply it with 1 minus AT square again to get your final matrix here, which filters the input, which is then B. And then your final new hidden state here is AT times the hidden, so AT times the hidden state here. So you multiply these two to get our intermediate one. And then we're plus 1 minus AT square times IT, and then times the XT. So here we're getting then the final value. And this allows us then to take the input filled, but we're not always multiplying with the same A here. Now, this AT depends via this RT on our input XT. So we have here an MLP which predicts that, and that is directly optimized in a way to filter out. And the same is for the for the input that is filtered by the input gate, which is again a prediction. So we are able to somehow control how much information we get from in our new hidden state, how much information we are getting from the input, and how much information we are getting from the previous states. Any questions to this? Yes?
So AT is always the diagonal matrix.
Yes, that is.
Isn't that severely limiting?
Yes, but I guess that is done just for efficiency reasons, that you can do that more efficient. And if you then do your hidden state in a large enough size, that could be possible. But I agree, I mean, there's a lot of hyperparameter decisions again there to whether have more parameters or less parameters. But in this case, they assume that this is the best performance. A different way, which is motivated a bit by attention, is what's called RedNet, which uses some type of linear attention, where the A is here just always a fixed discounting factor, and then we are combining our xt with two different weight matrices. So what we are putting in there is always different. So you see that from the nomination, we are generating again like a key value and query, but now the big difference is the keys are not compared to all values. It's only the current key and the current value are combined into each other. And that gives you here the hidden state is y times ht minus 1 plus x times wk transpose xt times wv. So here you have your matrix B is again depending on x. The matrix A is some fixed parameter. So you can't really learn a reset here, but it's just to discount it. Therefore, you have here by your query matrix is mainly your C matrix. So with this one, you're now again like deciding what you put into your output. So you have here a query matrix which is multiplied to your hidden state. So in this case, we are not controlling before, we are controlling A and B. In this case, we have dependence on B and C to do this type of control. Any more questions? And the last thing which got quite famous we will look into a bit more, is to go into continuous time state space model. So the idea is, of course, our work is like we're working in the discrete space. So we always have like at discrete points fixed points. However, we said there's also like the continuous version of that, which can be defined as with a derivation equation that h prime t is a times ht plus bt times xt, and then y is this. And now you can try to sample this function at different positions, and that will give you then the discrete version. And that is again what is like implemented in this Mamba paper, which is one of the most successful current versions of state space models, where they try to use this duality of like sampling at specific position, and this is part of the parameterization, like where you sample in order to get again your HTs and BTs. So how does it look? So let's look a bit more on what these continuous time space models is. So what we want to do here is we want to learn a good matrices or a good model that is trying a good approximation of our original signal. So we have the black one here. I hope you see it a bit. Here is a black one. And then you have the red one, which is the approximation. And of course, you're now approximating your signal with a fixed number of parameters, so you can't perfectly approximate it. But the motivation is now to get an approximation which is very good as a near future and then still decent the further away. But you see, it's getting worse the further away. And that is all the way the idea of these types of models, that you have a very good approximation here and then a less good approximation later. And that is somehow, in a lot of processing things, of course, makes also sense if you think about both vision processing or audio processing or text. I mean, far away information are important, but typically the information which are nearest are somehow the most important information there. So it's most important that you're somehow able to rightly try to predict these types of operations. So that is the way, and now we're looking how we can go from the discrete to the continuous space. So as we're seeing here, we have on the one hand the discrete version, which is hk. This is exactly the formula we had before. On the other hand, we have the continuous version as before. You can map between these two versions, or I mean more from the continuous to the discrete, by you can sample now points where you take your signal, and that will then give you here the h case and the x case and the y case. So the idea is that you're not having like a fixed sampling as you maybe have, but we want to have sample at different positions, and thereby we'll also control that. So again, you can once do your prediction in the continuous space, or you can make your prediction in the discrete space and use this type of model then to do this type of prediction. So the question is now again, well, how do you parameterize our previous models we had before in this case? And we're using some type of a bit special parameterization in this case. So we have A as a fixed one, which maybe looks now a bit weird that we have one fixed A parameter A, because we said like it's important that we have different AKs. But the thing of getting different A's is now that we are learning BT and the sampling time based on X. So what X mainly decides is on the one hand our signal BT, and on the other hand how often we're sampling our symbol. And based on that, we can then calculate our matrix AK and BK. So AK is then just exponential of our sampling frequency, sampling time A, delta AK times A. And BK is AK minus 1 times BT divided by A. How does it now influence a bit? And the interesting thing is here, especially the sampling, and there we'll see that this sampling frequency is then, or like the sampling length is like controlling this type of filtering again. And in a quite intuitive way. So the one thing we wanted to do is we wanted to do like filtering, so that we can somehow ignore inputs. So you want to do like that some inputs might be junk text, so should be ignored. How can we do that? The nice thing is now with this type of parameterization we have up there is that we can do that by just predicting delta k, which is 0. Because if our delta k is 0, then our AK is 1. So we're mainly taking the same hidden state. And our BK is 1 minus 1, which is 0. So that means in this case, the B is 0. So we are ignoring this input. So in order to ignore the input, we just have to predict delta K, which is 0. And then our parameterization will lead to our HK stays the same and our BK is ignored. So by doing that, we're just staying at the same position, which also makes sense. So if you sample several times at the same time, you're not really progressing in your continuous space model. The other idea is that we want to reset the history. So that maybe all previous things are not seen. Now you're doing filtering by setting the delta K to 0. Do you have already an idea if it's visually clear, like a motivation, how you could now set your history by predicting which parameters? Any idea? If you think about the sample length, how would you sample it if you want to like ignore what was happened before?
Long sample.
It's not even really wrong. So what you just do is you're taking your sampling length to very long. So imagine if you now have a very long time you didn't sample and then you sample again, that somehow means all the previous things aren't there anymore, they're forgotten. And that works here mathematically even again, So if your delta k goes to infinity, then here you have your ak, which is the exponential of infinity times a, and if a is negative, this is not zero, sorry, then this goes to zero. So you're having then like you're mainly saying your ak to zero, and therefore if your ak is zero, it's mainly then only taking your bt. So you can somehow filter by setting your ak to by setting your delta to a very, very large value, then this value is somehow ignored. Good. Then we want to go for a last point a bit on efficiency again, similar as we did it for transformers. But before we are doing that, do you have any more questions to these types of models? Good. So just like, yeah, very brief. I mean, one intuition of state space models, if you remember, was that we wanted to be more efficient. We didn't want to like do the quadratic calculation always, but we want to store everything in some type of hidden space. So the question is, are we now really doing that, and how we can do that? And we will see we'll need to use a bit of different techniques. So what type of data do we have in total here again? And here's like all the things that we somehow need to store in our GPU again. So the first thing we of course need to store in training is we have to store our input x and our output y, which has a dimension. On the one hand, you have the length, so the sequence length, and the other one is the dimension of each data point. And for simplicity, now let's just assume that these two dimensions have somehow the same size. And then for Mamba, we have our parameters. These are like on the one hand parameters for the time, that's deltas here. Then we have our BKs and Cs here and our As there. What we will see, what we also have is that we are trying, in order to have we have this limitation that we only can store fixed size. That's maybe in our hidden size, we want to have as large value as possible. That's why we introduce the extra dimension going now back to store additional information during our hidden state. Because we are limiting ourselves in a state space model, we cannot look back as far as we want, but we have to somehow store always everything in our hidden space. That's why it makes sense necessary to like give there increasingly memory. Based on this one, we then in Mamba calculate here our values a, b, and h, which all depends on the time. So but they also have a lot of parameters in there. So these are the largest chunks. And that, of course, we now somehow have to address in order to like do this types of efficient calculations. If we're doing that, the naive one would be, so we start with B, delta, and A. Then based on that one, we're calculating our A square and B square. Then we're taking our input, multiplying it always with the A and B values. We're getting our H, and then we're multiplying this one with the C and getting our final value of Y. And this might, again, be not really efficient if you have to always load and unload. So there was an idea of how to do that better. Do you remember what it might be helpful? So what will we try to do there? Should think about flash attention. What was the main motivation there?
We load the pieces you need for one complete calculation of a part of Y.
Yes, exactly. So that you're again doing here. So you're doing fuse operations. So you're not doing one operation or the other, but you're taking your current input based on that one and your previous parameters. You're calculating A square and B square for this one, calculating H for this one, and then maybe calculating X for that. So you're trying to do exactly this type of calculation. In the memory network, then that looks like that in your GPU memory, you always have your HTs, and then the A's, BTs, and CTs they might be loaded from offline from the background. Okay. So again, you're trying to optimize your calculations, and that's also why you take these parameterizations, that the BTs, for example, can be directly calculated, and you don't need to store everything in the memory. Good. With this, we're somehow at the end of the state space models. Do you have any more questions on that? So we learned now three or four different types of architectures: CNNs, RNNs, self-extension, and state space models. And all of them are mainly there that you have an input sequence and you can generate a different type of sequence. And you can use the global or local context to disambiguate things to do the processing. And we saw they have different advantages and disadvantages. And therefore, like, some of the next step is now to look a bit at them. First, what can we do with them, how they are different, and that we want to do like in now the last part of this lecture on architectures. So I need to shortly switch. Okay, the date is wrong, but otherwise. So with this, we want to go now to the last part, the seventh part on sequence models, and that's some of the last part on architectures now. So what do we want to do? We'll first start with an overview a bit on what sequence models were discussed. Then there are some additional things which are interesting. First, we learned already at the beginning that, like, typically networks are deep and deep learning has multiple layers. So we'll shortly have a look how to stack them up. We'll look at what properties the different have so that you get a bit of feeling what are the pros and cons. And then we'll look at some type of applications. And one important application, which we haven't talked about yet, is like conditional generation. And then we will also see where especially the thing is that now we always assume that all data is available, but this is typically not, it depends on the application. Often this is only true in training, but not in testing. And especially that is the case for conditional generation. That's what we want to look at. And then there's also an important notion of like how you process the information. And there's a quite significant difference in RNN style models and transformer-based models. And that we want to look there too. But let's start with just general sequence models. So in general sequence models, we have these one-to-one mapping. So what we're having is we have input variables of this X, which is on the one end, we have the hidden the input size N, and then big N is the number of elements in there. And we have what we call this one-to-one mapping from the beginning, where we map the input to the output and to do that. And so we're not changing the structure in that way. The same input structure is always also the same output structure. Might be that the hidden size changes, but this is not really essential. You can always change the hidden size. So we can just assume that it's like somehow the same type of size in there. And then we learned different types of how we can do that, because we have the problem that now a neural network is not easily applied because we don't know how long the length is. So if you unroll it, it's unclear how long this is. So you have to, look at some things, how you can process things that you're able to handle different lengths input. And there's now the ways how to do that. The one is the TDN over CNN style, where you apply the same operation at each timestamp. So we're always looking then at these three input values, for example, and we are always applying the same thing on them. The other idea was presented by the CNN, where the idea is that we're always storing everything in a single context model, and then at each time process, we are looking at our context and at the input and processing the thing the same. So at each time step, we're taking this one, calculating it again, taking this one, calculating it again, taking this one, and so on. And then we had two versions from that, the traditional RNN, where we have nonlinear representations here. So how this state depends on this state is a nonlinear one, while in a linear one, these are linear representations. And that gives us, on the one hand, now a connection to the CNN, and we see a huge now advantage is what was a disadvantage in RNA, in general networks. If you remember at the very, very, very beginning, we said, oh, nonlinear operations are very important in normal neural networks. Do you remember why? Yes?
Preserve that multi-layer effect, because otherwise you could reduce it to the single layer and you can't implement all logic that you.
Yes, exactly. So that was a big advantage of multi-layer, that if you don't do multi-layer, everything like can be especially also expressed by one single operation, and then you don't have the advantage, and we saw the XOR problem. Now we're using the same effect here, just in the time dimension, but to a positive effect. So in the time dimension, it's again, so if we're doing like nonlinear, they can't fall all together. But you saw now that also has, of course, an advantage if it falls all together, because then the order of the operation is no longer important. And in LTI, so in state space models, we saw now the big advantage. If we're doing that, then we can calculate them in different ways, and we can do a lot faster calculation. So what is maybe for the expressiveness a disadvantage is now, of course, for the calculation a big advantage. And if you see it here, it somehow also makes sense. So of course you can view that this one depends on this state and depends on this state and depends on this state. But you can also view this one out, just like some preliminary computation that you did. So in reality, this one just depends on this, and this. And that is a training view of the LTI, where you say, yeah, they are directly depending on these four, and that's why we can do this calculation directly and fast. While in training, we are storing, in inference, we are storing this intermediate information to do process-wise. And then there is the last one, or the other one we looked into, is then the self-attention networks, where we had a bit of a different view. So in this case, we always had this query key and values for each of our inputs, query key and value. And then we always do a new summarization of all the inputs based on our current query, compare this query to all keys, get similarity values, multiplying the similarity values with our values, and then do the weighted sum to get a new hidden state. So here we have one hidden state. How did we get a hidden state for each input? Yes?
Use different query for each number.
Exactly. So we are now using this one as a query to get the next hidden state here, and this one is a query to the next. So again, we are not changing the structure. So the input is directly used for the output. The big difference is now we're not somehow storing everything, but we have somehow information flowing from everywhere. So each hidden state is influenced by each other hidden state. Okay, before we are looking at these properties, maybe one more point. Of course, if you want to go into like building large networks, it is essential that you're not using one layer. And especially, for example, transformer is really like only working typically with quite a number of layers. So how does that work? You add additional capacity in the same way as we had for feed-forward neural networks, by just having, for example, a multi-layer RNN or any other. And the only difference is normally here you have HT depends on your previous hidden state and on your input and your parameters, and that's how you calculate your new hidden state. In an RNN now, you just replace the input by the previous layer. So in layer L now, the hidden state depends not on the input, but it depends on the previous hidden state in the same layer plus the current hidden state in the previous layer. and then your parameters. So you see this blue one here depends on the one hand on the same, on the previous hidden state in the same layer and on the same time step in the previous layer. So these two blue ones lead to this new hidden state. And this is now, of course, you see already easily extendable. So you're doing, you can do any type of layers in there. Typically, because you want to learn different types of functions, there's no sharing between the different layers. So these delta L's are only used for the current layer. So you have parameters for this layer and for this layer, which is possible because we are predefining the number of layers. So we are saying at the beginning, we have 5 layers, and then we can each example is treated by 5 layers, and we can apply that. If we would want to do like variable size steps, then of course this doesn't work anymore. So then you have to do something different. But the normal thing is you have exactly the same type of hidden layers everywhere, and this calculation can then be done there. Good, but in addition to have additional, so what you're here doing by stacking layers, you make the model more powerful. It has additional computation, especially it might be able to get different types of information or more complex operations and so on. You can also do some types of, with multiple layers, you can do other things. For example, if you can reduce the sequence length, and especially you can also increase your field of view. So both you see here, so we have an input size here of 10 things. And the first thing is, since we're doing twice an operation with some shift, we are reducing it to a sequence length of 2 in the top layer. Furthermore, here we have a kernel size of 2, and here we have a kernel size of 3. But you see that the joint kernel size is now already 5. So by combining different layers, you can have a more and more global view on that. If you would directly go to a kernel size of 5, you might have very big number of parameters, and so you can do stack-wise, like slowly increasing your receptive field in that one. Good. Any more questions on this? Good. Then let's have a look at the receptive field. That's one important thing. So we have 3 different types of receptive fields typically. So in TDNNs and CNNs, we only have local context. We already mentioned that at the very beginning, that in this case, you only have context there and you can only look at that. You cannot look around that. Doesn't matter how long your sequence is, you will always look only at some part of your sequence. Then you have the RNNs, or the state space models. In this case, in the middle here, your receptive field is always all previous parts of the sequence. So in this state, it depends on these 3. Either now it's depending again the view. You saw that if you're doing this calculation, which we saw for the nonlinear, you directly see that this one depends on the 3 inputs. If you're for an RNN, you see that via the hidden state that they depended. So you're always only looking to the left and never to the right. For self-attention, in the default one, you're viewing on everything. So each hidden state, we're saying one important property of that is that each hidden state depends on all the other hidden states. So we have this fast information flow that directly from every state, we have information flowing to all the other states. Good. Any questions about this? Good. There's one more property, and that's the notion of direction. And we'll come that is, especially for some models, very important. So there's a big difference again on the RNN and the state space models. We have this notion of direction. You saw there is a difference. The model looks to the left and sees everything to the left, but it doesn't look to the right. So there is definitely, we always have processed everything up to the current point. While for TDNNs and self-attention and CNNs, this is not. There is not really a direction. If you look at that, there is not clear. It's just looking either at everything or as a part, but there is no clear definition that's only looking in the backward or looking in the forward. So there is no direction in this one, while there is a clear direction for the other one, which separates always your input sequence in the part that you have already processed and in the part that hasn't been processed until now. And this has, especially this direction, has an important issue when we're thinking about the application. And there is two typical types of applications that these are applied to. The one thing is what we call an encoder. In this case, you have some type of information and you want to encode this input into a hidden representation. So in this case, you have your text here and you're interested in learning some type of hidden representation that is representing your input. And again, if you come back, that's why I meant the notion of direction. There is now an important thing here. We're typically having all information available. So we know everything that we want to encode. There is, of course, there might be situations where that is not the case. Any idea what could that be? If you think, for example, of audio or speech processing. Yes?
Decoders and decoder interpretation.
That decoder will come soon too, but even for encoders, there is special type of encoders where not all the information is available. Yes, somehow in speech data is a typical application, but not all speech, so it depends. We call that often the online processing. So in offline processing, you have everything. But if you think about speech recognition, speech translation, or something which observes, then you only have encode what you have seen until now. If you not have to do a prediction about some old data where everything is available, but when you continuously try to understand what is currently said and predict the translation, the transcript, or something like that, then you might also have this type of encoder where not everything. But the typical application of an encoder is where everything is available in an offline processing. So you have everything available, and then you want to encode this to have here a representation. And that is the main approach of your sequence layer, is that it takes this representation and it generates a new representation, which is somehow better representing what you all have done. So this representation should be somehow more have more information or better matching information that represents what is helpful for you. And the other type of sequence labels are so-called autoregressive decoders. In this case, if you want to generate a structure, so let's see at least, say, for example, a sequence, what is currently state of the art and working best is that you're just predicting each element one by one. It should be integrated here, shown here. So you say, oh, start to generate something. Then it generates today. Then you tell the model, oh, you generated today. And then it generates the next one. It generates maybe I. And then you tell the model, oh, the last token was I. And then you generate again. So here you have the same type of sequence layer you hear. So in both cases, you can use everything we did. But there's a very different type of processing, because in training, maybe you have everything available, but while generating, not everything is available. You're processing the first one, and then you're telling the model, this is the first one, and then it's generating the next one. So this is why it's autoregressive. You give the model itself its output again, so it can understand what is the tokens up till now, and it should do the next type of processing. And on this second part, we want to look now for the rest. You see already this is a bit what is a typical language model, and therefore also large language model looks like. And we want to look into what does that affect on your architectures, because we have to do a bit of different types of combinations of sequence layers to do that. And And yeah, and we are typically more interested in now conditional generation than just generation. So typically you're more interested in generating something based on some input than just generate some random text. I mean, that is maybe you'll see later used for training, but in generally in applications that just generates you random text might not be super important. More interesting it is when you do conditional generation, you give them some input and then you want to generate something based on it. What are examples for that? So there's different examples. It can be, for example, machine translation. You're giving as input the sentence in one language, that's your condition, and then it should generate a language in a different language. And it can be a dialogue model. You're giving in the user's request, or maybe the whole history, and then it should generate the answer to it. There's also things like text to image, where you give it an image and then it should generate a description. So it doesn't need to be all the same modality. It can be that the one is an image, which is maybe 2D, and you want to generate text. Again, that is a nice thing about this type of deep learning approaches, what we have seen already at the beginning. Everything is represented somehow in some hidden states. So there is often the possibility to combine them and like generate one representation based on the other. And the other one is automatic speech recognition, where you want to generate text of the audio. Again, you have an audio sequence as input, and you're generating a text sequence as output. So how does this type go? This type work? And we'll see there's mainly currently two big types of models how you can do that. The one is based on what we learned before is like what is called the encoder-decoder model. And the idea is that we're like combining both. So on the one hand, we have the encoder. Now imagine we have like the task of question answering. So you ask where is Karlsruhe, and the output should be hopefully in German. So if you want to do that, you can have in your neural network, which should get as input where is Karlsruhe, and then it should generate in Germany. You have an encoder which tries to first understand the question. That is the encoder part here in blue, and then you're generating the output part there. So what you can do is you put in your sequence here. Then you can do any types of sequence model here that tries to understand that, and that generates here your hidden representation, which explains now what that should be. And this you can do in parallel. So here you have always all information available. So you can do in order to generate this hidden state, you can do this hidden state. And in order to generate this hidden state, you can use all the others in there. Based on that, then you have a decoder which should generate word by word that it's in Germany. So what you do is you say, oh, start with your answer. That's the start symbol. Then you let your network run. It will generate the most probable token, hopefully maybe in. Then you tell the model, oh, start the sentence with sentence started in. It will again put these things in and will generate Germany. You put this one in again, it will say Germany, and then you generate in Germany. So in this case, now you see, of course, in order to generate Germany, you can't access Germany here because you haven't generated it. So in this case, it's important in a decoder. A decoder can only look to the left because only that has been already generated, while the right side has not been generated. So here you have to consider the direction, while here you not have to consider the direction. So now you have here two types of models, the encoder and the decoder. What is now the challenge? Maybe it's too obvious. We need to connect them both. Somehow, I mean, you need to have information flow from the one to the other, because information here, what the question are needed to generate the answer. Even, I mean, we're now assuming the model has seen a lot of Karlsruhe, so it knows that Karlsruhe is in Germany, but it needs to understand the question in order to generate the answer. So we need to combine these. So here you have a sequence model, and here you have a sequence model. Do you have any ideas how you can connect these two? Like what type of architectures you can use to connect two types of sequences here? Any idea? One thing we even had already in the lecture. Yes?
Two approaches. First one is what we already talked about, the comprehension architecture. Second one would be how to do it in RNN style, just transfer the hidden state, locked hidden state as the inputs to the decoder.
Yes.
Locked instead of the encoder to the decoder.
Yes, exactly. So the one thing you can do is you can have here an RNN. I'm sorry. You can have here an RNN, which goes, and then in an RNN there is a direction. So the information are mostly in there. So there should be all information in there. And then you can just either copy or you can do a linear transformation to an RNN here, where mainly you say, oh, the first, instead of, normally in an RNN, you always have the initial hidden state, which maybe is always 0 or fixed. Now you initialize your RNN not with a fixed thing, but you initialize it with the information from the encoder. So then the model learns that it now should generate the input based on this information. So you have this vector here goes as starting point to this vector, and then can do all this type of calculation. And this can be just a copy, this can be a linear transformation if the dimension is different, that doesn't really matter. But the main difference is that your RNN is not starting from scratch now, but you somehow initialize it with being H0 being gotten from your thing. So you're conditioning it on your encoder. Can you do that only with a RNN encoder? Or could you also do, how would you do it if you have a different type of encoder? Or is it not possible? Any idea? So that's not easy. So if you have a CNN, I mean, you could do also a CNN here on the input first. You can have a CNN encoder, which gets everything, and then we're getting their sequence. How would you there also take some of the last hidden state here and put that to your RNN? If this one is a CNN-based encoder. Yes?
Could I just use the last state because it's the slope view, and so the first states are just not represented, but then you would have to just connect all of the output to your decoder.
Can you do that easily? If you think about this is your initialization. So the first part is completely correct. So that's not a good idea to take the last one. But can you take all the states and put them here into your hidden state?
You have to merge them first. Yeah.
How would you merge them, for example? Exactly. Pooling would be a typical thing you're doing. So what you would do, you pool across the time dimension. So if there's now each one here has a dimension of 100, you would pool them all, then you get one vector of dimension 100, and that you can put into there. And that will work good. How about self-attention? Could you also do self-attention in your encoder? Would you take the last one, or which one would you take then? Yes?
I mean, by just doing the cross attention. By having a query going over all encoder.
But if your decoder if your decoder should just be an RNN. I mean, otherwise you're right, we're coming to that on the next slide. Yes?
It's the same case as with the CNN, we can do pooling over all of the hidden states.
Yes, exactly. So we would have to do a pooling over all of the hidden state. If we would take the last hidden state, it's not as clear anymore. It depends on all the previous one, but since the query is from the last, it will somehow focus on the last input. So it might be better to just do some type of pooling, and then you can do that. There is for self-attention, there's also sometimes extra token which are trained to summarize the whole sequence. Then you could also take this type of token. But as you pointed out already earlier, if you're now on the decoder side, have attention, then you can also do it differently. You can take your hidden state as a query, you can query all the others, and then you can do do the weighted sum and use that here again. So you can do the cross attention from the decoder to the encoder and thereby do. That again has the same advantage. Before, always the same information are passed from the decoder. They are once passed. So once you pass information from the encoder to the decoder, and they are then always taking. It doesn't matter how long your sequence is. You will always only get once all the information passed. If you do cross attention, at every time step, you'll do a cross attention. So at every time step, you get other information from the decoder and can use them. And then on the decoder, I mean, if you're doing anyway cross attention today, you would mostly do also there some type of you would do there some type of self-attention, but of course you can also do other. You can do RNN. So you can also use your RNN to do the query and get the information there. That depends really on what type of architecture you're interested in. Good. So this is the one type of architecture. Before we're going to the other one, do you have any more questions? The other idea is what is called decoder-based models. And there, we're not doing a separation anymore between decoder and encoder. We are saying, yeah, the decoder has a bit of the limitation that it like only can look to the left, and because it has generated that. And it's also generating. But while we can view this one also as one sequence where we first have the input and then we have the output. And for the output, we are also interested in what it will generate because it will do that step by step. For the input, we're not generating anything. It doesn't matter. We're just wanting to somehow encode everything here in your representation. So you're encoding everything in here, and then with the same model, you're generating. And you can do that with an RNN now on the decoder. With a CNN might not be super good because you only have local context and you want to, I mean, to do the answer, you have to somehow look at all the source, but you can do RNN, LTR, like state space models or self-attention, anything. So you're simplifying this thing by not having two different models. One is processing the input and one is processing the output. But what you're doing here is that you have the fixed input, which is completely there. And then one by one, you're processing the output there with the same type of model. And this is, for example, how like more large language models nowadays work. This in front here will be the prompt, like how you prompt the model, what it should do, and then you're just continuing to generate things. And you can see this is somehow very similar to this one. If you look at this one and you just assume that this one is the same RNN, the encoder and the decoder, then you have a decoder-only model because it's just going through everything. Good. We are now want to talk a bit more about the information processing. That will be the last part for today. But before we're doing that, do you have any more questions? Good. So we're said for the encoder, there is all things are available at the beginning. So meaning you can do, of course, unidirectional processing. You can process it from left to right. Even if everything is there, it's not stopping you to ignore dependency on the futures, but you're not limited to that. So you can do unidirectional processing, or you can do bidirectional processing where you use information for both directions. And of course, somehow it seems that if you can do from your data side bidirectional processing, it might be beneficial because you're faster getting that. And that's why people looked into like, can we do all the architectures with bidirectional? We saw that self-attention is automatic bidirectional, so it looks at both, but RNNs are only unidirectional. So meaning we saw that, yeah, they are depending only on the previous one. So can we somehow add bidirectional information to this type of network? Do you have any idea how that could be possible? Yes?
Would we reach a whole network and then encode that information and then later lock that?
I think that's mainly the idea. I will just phrase it a bit different. So what you can first do is you can just do the backward pass. So that I think what I meant with the sphere. So instead of having a forward RNN, you can of course also define a backward RNN where your hidden state depends not on the previous states, but only on the future states. So what you're just doing is you do your initial state at the other side and do the processing the other way around. Or if you do it from the formula, so the hidden state here depends on the previous hidden state and xt. Now your hidden state depends on the next hidden state and on the input. So it depends on this one and this one. And then you have now one forward pass and one backward pass. Now, can you just combine them and make this hidden state here depending on the previous one and on the next one? Maybe that would be the easiest one to do a bidirectional one. You just have now a function f, which depends on your input, on the previous hidden state, and on the next hidden state. Would that work?
Oh, at some point you need to compute one of them in order to be able to compute the next one.
Yes, I mean, at least it's not easy to compute. I think there are formulations if you formulate it again with derivation equations, there is some solutions to that, but it's not easy because exactly as you said, here it's easy to calculate that. We need this one, but this doesn't depend on the other one. So it's easy to calculate. You have an order in which you can calculate. If this one would depend on this and this one would also depend on this. So they would both depend on each other, and we can't easily calculate them. So that wouldn't work. However, in networks, there is an easy thing around that. We can just glue these two networks together. And that is what people typically assume as a bidirectional network. So we have a forward directional network, we have a backward directional network, and both give us hidden states. The hidden state of the forward pass and the hidden state of the backward pass. And now you're just concatenating these two hidden states. And now, yes, the lower part only depends on the previous one, and the upper part depends only on the future, but the concatenation depends on everything. So now you have here a hidden state, which depends both on the past and on the future. So with this type of bidirectional RNNs, you're able to, for example, in encoders, they were used quite a lot because they have the advantage that they are able to process everything which is available. And then in order to disambiguate or to understand this token, you can look both at the past and at the future. And both things might be helpful. There's one caveat a bit with it. When you think about the model, what might be a bit of a disadvantage of a bidirectional RNN?
What about the layer information? So that the information that is processed by an RNN at the start of the sequence is less important than the one at the end, because you look at the end state. Right? And if you do that in three directions, you wouldn't get hotspots of information. And for example, the middle had very little information about both of the ends.
That is true, but I mean, that's a bit what you want. In order to understand the middle is the most important. So you have mostly our information from the left and right, and the far away are off. But that's a bit also what you want. I mean, it's getting a problem sometimes. That is true, that very far away things. But I mean, it's at least better than the unidirectional information because they have also less information about the beginning, but you have no information about the future. So you have already an advantage. At least you have information about the near future, and the faraway future, maybe not too much. But you have to, I mean, what maybe is a bit of a disadvantage, you have double your parameters. So you now have parameters for your forward and for your backward pass. So it's definitely, you cannot also like do a network which sometimes has forward information and sometimes has bidirection. So there's different parameters for the forward and backward pass, so these ones, and therefore, you cannot like easy like switch. Oh, now I do forward processing. Now I do backward forward processing, and so on. Okay, so this is for the encoder. Now for the decoder, the picture is a bit different. So for the decoder, we already said we are doing autoregressive decoders. So maybe it has to be an autoregressive decoder, but just for a lot of applications, that is important at the moment. There's also non-autoregressive decoders where everything is done in parallel. That it's not, but for autoregressive decoders, you're generating token by token, and that means we need a unidirectional model. We are not allowed to look into the future. If you remember from the answer we had before, when you predict Germany, you shouldn't know that the next word was Germany, because if you look at the future, things are too easy. So if you're looking, I think it's a bit away. We had this example here. When you generate here Germany, you're only allowed to look at the past. If you have like in training, you use this information, you look into the future, that is not available during inference. So you're not, during inference, when you generate, you only are here. So you cannot look into the future. So you also shouldn't do that in training. So we somehow need a network which only looks into the past and not into the future. With RNN, this is straightforward. I mean, there we said the normal RNN is always unidirectional. However, now we learned self-attention is nice. So the question is, can we also do self-attention for that? So the normal self-attention is unidirectional. It doesn't have a direction. You'll always, to understand here now, the second token. So if your second token is a query, you're attending to all the queries here and then generating your weighted sum and doing that. So if you look at the queries and keys, you see that all of them are combined and they're all once compared. Each token is one a query and one's a key, and they're combined, and that is then used to generate the hidden state. So the query one, all these comparisons here are used to generate the first hidden state. All these are used to use the second hidden state, and so on. Do you have any idea how we can now extend it so that we can use it for a unidirectional model? Any idea? Yes?
You simply don't compare it to the keys which come after the query.
Exactly. So you can, and that is what is called then the so-called mask self-attention. What you're now doing in order to use a self-attention layer in the decoder, where you're only able to look into the past, is you're masking the future. So for the first query, it's a bit boring. You're only comparing it to yourself, and all the others is masked. Now for the second here, so you're looking at comparing to yourself and to the previous one. But these comparisons you're not doing. Doesn't matter. I mean, it, of course, in some way matters in a way that your result is different, but from the computation, that is no problem, because now you just do your weighted sum here with less elements. So at the second position, you're only combining 2. At the third position, you're combining 3, and in the fourth combination, you're doing all 4. So you're just like leaving out some comparison in here and not doing that. And that will directly allow you to have now a unidirectional model. So there's a big difference to the RNN in that way, that here we not have now different parameters. So how we going from a bidirectional model to the unidirectional model is that we're just setting some things to 0. And then we're only looking into the past and not into the future. And that is the so-called mask self-attention, which is used in all of current like large language models, because you have there in a large language model, it's only a decoder, as we say. So all the things you're doing is like this type of attention to only the previous tokens, because if you predict the next tokens, you cannot attend to them. I mean, one maybe thing to really understand them is good to look at the original work of the attention. So this is the original transformer-based architecture, and this uses all 3 types of attention that we have seen so far. So we now we started with a self-attention. We looked at the cross-attention already last time, and this time we used the mask self-attention. And in this one, we have all of them included in there. So let's go one step by step through all the transformer architecture. So here you have so the transformer is an encoder-decoder model. So you have an encoder which encodes your input, and then you have an autoregressive decoder which word by word generates your output. How you're doing it is you're starting with word embeddings, and then you're doing the positional information. We know that this is important. Then you're doing here a self-attention. Will it be a self-attention or a mask self-attention? What do you think? Yes.
The self-attention, since we got arrows and those.
Yes, exactly. So this is a self-attention. We have the encoder. It has a whole input available, so we can do normal attention. You see there, we'll later come in more detail to that. There is like a skip connection around that that's more for learning. And then it's combined with just a linear, with just a normal linear layer to do additional computation. So there is no information transported between different positions in the next layer, but just like each learned representation is further processed to do some position computation only based on the computation. Then this blue one is repeated for several times. So in the initial work, I think it was like 8 times. You stack these types of blocks of 2 layers 8 times on top of each other, which will give you then the whole like type of encoder. So you see you're having always an encoder layer, then a linear layer, and you have this residual connection around it, which just adds the input to the output. Why you do the residual connections, we'll see later in some learning. And this is your learning, so your encoder. So in the end, now you have for each input token, you have a new hidden representation here, which has learned a bit what this should be represented in this meaning, where you have information flow all across in all directions. Then you can do here your generation. How do you do your generation? Your generation you start with your word embedding again. So the first, if you don't have a word, you saw already you have the start token, which also has an embedding saying start generating. You add the positional information. And now in the decoder blocks, so again, you see here blocks, so you're stacking them over and over and over again. And there you have this time 3 different subcomponents. First, you have a self-attention here. In this case, it has to be masked because it's a decoder it's generating, so it only can look to the past, cannot look to the future. Then you have here the block of the cross-attention, where the encoder is a query and queries all the representations here. These are then the keys and the values, so you compare to and get back information, which you add with your previous ones. Then you have another linear layer on top of that, and that you repeat to like try to understand what should, based on what has been said previously, what has been generated previously, that is what you put in here, and what was a task which you get from the encoder. So you're combining 2. On the one end, your generation should fit somehow because it has to match what you have generated before. On the other hand, it should be nice because it has to be fitting that way. And this will allow you that then. And then you have here your token, a linear layer. And then finally, you have your output prediction. How big is the dimension here? How do you model the output prediction? Does anybody remember how we did that? This is just a probability distribution across then all the words we're having, and that says you for each word, what is the probability of this word? And now you also see a bit why you need an autoregressive model, because the model just predicts you a probability distribution. And then as a model, you can decide what to put in. So you can predict the most probable one, but then you should tell the model still, I selected this one and not the other 3, which were maybe equal in probability. That's why it's important to have this autoregressive way, because the model only predicts a probability distribution, but it doesn't really know what is the final one that got selected, and that you should put into then down there. Okay, any questions to that? Yes?
That means that transformers deal well with Gaussian modality?
Yeah, but I don't get why. So why do you think it's dealing well?
Because if you have a model and you can only do not probabilistic but deterministic output,
Yes.
then it cannot choose multiple modes by chance, which will mean that it always tend to one mode and try to learn that mode, and training kind of destroys the other modes. While with this, when you have a probability, you can set an output and you can sample from it, you can preserve the different modes.
The problem is then how you train it, because that is the problem. You're training it by making this probability distribution to one hot distribution, where because in training you only know the correct solution and not all you don't. I mean, typically you have example sentence. You don't know, oh, at this position it could be this word, or this word. But I think this is more about how you train the model, and this model is trained in predicting always the one which we saw, and I think that is maybe the major issue there.
Could also see sentences where you have the exact words. You could train multiple sentences that have the exact same words, except for one or two.
Yeah, I mean, that is happening, and the model can somehow predict that. But that is more a difficulty of it, because then the model doesn't know which one to select. I mean, that now depends. Should it generate all possibilities? Yes, you can do that. So you can do typically sampling, and that especially, for example, for dialogue, it's important, because if you have a dialogue, it's maybe boring if it always gives you, even for the same input, you shouldn't answer always the same. So it's maybe nice if it's not always starting with hello, but it sometimes starts with hello and the other time with good morning, and so you have different starting. For other use cases, it might be important to always do, but you can, I mean, since it's a probability distribution where it's deterministically calculated, you can also use that. So you have both possibilities in some way and can use both. Good. With this, we're done for today. I hope you got now with the last 4 or 5 lectures a good overview of different architectures and how they are different, how they're the same, how we can replace each other. You see that they're partly combined. There's also even like for Mamba style, so for state space models, often they are combined with one transformer layers, because that's still somehow more powerful. So it's also good to know a bit the combination. And based on that, we'll then go to the next part of the lecture on Thursday and look into how to train these types of models. There we have it.